We have already seen some semantic segmentation datasets and its applications. In this lecture, we will explore a widely used neural network for semantic segmentation, which is the FCN, or Fully Convolutional Neural Network. Unlike the convolutional neural network we previously introduced, an FCN transforms the height and width of the intermediate layer feature map back to the sides of the input image through the transposed convolution layer, so that the predictions have a one-to-one correspondence with input image in spatial dimension height and width. More concretely, given a position on the spatial dimension, the output of the channel dimension will be a category prediction of the pixel corresponding to that location. Let's take a look at the details for FCN. So FCN was proposed by Long et al. From UC Berkeley in 2015. So here is the full landscape of this task. It has two folds. So the first half takes an input image from below and feed it to a series of convolutional neural network and polling layers, which then shrink to one scaling vectors in the middle here. And then the second half of the upsampling outputs the semantic segmentation mask, which makes sure the output size matches the input size. And the commonly used method is called transposed convolution, and we will discuss more in the next slides. Well, fundamentally, the last layer of FCN is to apply a softmax to each pixel and predict the classification mask. Here comes to the details of transposed convolution, which is also referred as the upconvolution or deconvolution. Well, in FCN, the transposed convolution is used to upsample the feature maps to match the original image size, which is in the visualization here. We apply this 2x2 transposed convolution kernel on each cell of the 2x2 input matrix. Then we sum up this dot product together into a 3x3 output. So how do we obtain the kernel parameters? Well, similarly to the traditional convolutional neural network, we can initialize the weights and train them through optimization algorithm, such as gradient descent. We usually initialize the weights from a simple upsample techniques called bilinear interpolation. I won't be too verbose here, but if you are interested to the technical details of bilinear interpolation, feel free to click the link and check it in detail. So the original network of FCN has encoding convolutional neural networks to shrink the feature down and use the decoding sampling techniques to amplify the feature up at once with this 32 by 32 upsampling kernel, also called FCN32s. Well, FCN also applies a trick called skip architecture that takes advantages of the full feature spectrum, and the skip architecture views the feature hierarchy to combine diff, coarse, and semantics information, and shallow, fine appearance information. To be more concrete, rather than only apply the 32 by 32 kernels to the Conv7 layer, we can grab the POL4 layer and plus the 2x of upsampled Conv7 layer, and then we apply a 16 by 16 upsampled kernel to this summation to get the final 16 times to upsampled predictions, or also called FCN 16s. Or we can go down to even more granularity and apply this FCN 8s, that is to extract the information directly from the POL 3 layers and plus with these 2 times of upsampled POL 4 layers and 4 times upsampled Conv 7 layers. With the summation of these 3 layers, we can apply 8 times upsampled predictions. And these tricks give us super great result because the spatial location information is kind of lost when the convolutional layers are going deeper and deeper, and hence the output from the shallow layers have more location information. And if we combine the both, we can enhance the results of the predictions. So the FCN networks was trained on the Pascal walk dataset that we introduced in the semantic segmentation introduction lecture. And the common evaluation metrics we used are the pixel level accuracy and the mean IOU, which is the mean intersection over unit. With this matrix, the FCN8 model performed the best, and we can train the FCN with different convolution networks such as FCN XNet and FCN VGG16, etc. And here are some results of the FCN, where the left ones is the original image, and the middle ones is the ground truth label, and the right ones are the FCN8's predictions. So I will not show you the details of how to train an FCN model in Python, but here is a handful link for you to explore if you are interested.